think we're all reaching a point in the semester where the amount of fucks we have to give is rapidly approaching zero. And my computer is hung up because of course it is. Because it is a surface and it is by definition a piece of crap. So how's everyone doing? Might try and solve technical difficulties.
Very tired.
I'm okay, thank you.
Yeah. Are you not sleeping, Paul, or
Just the puppy bathroom breaks in the middle of the night getting to me, I think, and I spent yesterday painting.
Well, it doesn't sound like fun.
Yeah.
Okay, I think my PowerPoint is just acting up. Okay. Sorry, just take a second. I'm gonna just kill everything and start again. Oh, but it doesn't think that PowerPoint is open even. Oh, there it is. I don't think you jinxed it, Ashley. I think it's just stupid. My dog pulled out he got overexcited this morning, and so he pulled out the power cable where my tablet was charging, so my tablet was dead. Because he plays under my desk and chews things. I don't pay too much attention. So far, he doesn't chew cables. Though the only reason I'd really know is if like suddenly I either had an electrocuted dog or my computer stopped working or something. But he pulled this one out. There we go. It feels like forever since we last chatted. It really does. I just haven't slept a lot. Okay, there. I think. Oh, but I'm not sharing my screen because as far as the pandemic, I still don't know what I'm doing. So when we dropped off last class, Paul had asked us a question about copper binding to triple bonds, but we had just spent some time talking about introducing the idea of Carolyn Bertozzi and the copper-free azide alkyne cycloaddition that relies on the torsional strain of an 8-membered ring. There's not a lot to say to it, actually. It does the mechanism that you think it's going to do. I'm going to create a new presentation for this today. Okay, it's going to be, I guess I'm doing it in landscape. That's fine. But I don't have enough slides. You can tell I think I've slept like a total of like 8 hours in the past 60. I'm really feeling it. Okay, so click chemistry continued. So what I'm going to do is I'm actually going to teach towards the exam in the last 2 lectures. So you have everything you need for that. Why is it not working? Maybe you did jinx it this time, Ashley. Oh, kick me back to my main screen. Okay, let's try this again. So that's really ugly. So if you have an azide and you have some form of cyclooctane, the electrons just flow from the negative to the triple bond, which then pushes the electrons onto this nitrogen, which can then move the electrons onto the middle nitrogen. The reason it can't attack the middle nitrogen itself is because that would mean the middle nitrogen already is using all 4 of its orbitals. It doesn't have any orbitals available to accept more electrons. And you get the triazole. And as we were talking about last class, this is really, really innovative because suddenly you can do this kind of chemistry and couple dyes and things together in like in living things. And last class I said the tRNA stuff with lysine. I got the wrong guy, the wrong bald middle-aged white man at Scripps, which really doesn't differentiate. They're all bald middle-aged white men. I meant Peter Schultz. I think I said Brian Stoltz, but it was Peter Schultz. I think. Unnatural amino acids. It was one of those things where I was like on a walk with my wife and I went, shit, I gave them the wrong name. Not that anyone will actually care, but if you are looking it up at some point in the future, you're going to be Schultz. Anyways, I think that's what I want to talk about with the azide alkyne one. But there's a few other reactions I think we really should cover in this kind of thing. One is, and I'm just going to make sure I've got everything open. So if you take a look at one of the papers I sent out on there, I'm not sure if you've taken a look at them yet. Hopefully you have. I think one of the most useful papers that's currently available in the literature, and I need to find it again, is the Tang paper from 2014. And it's basically an overview of the state of the field at the time. There has been some changes since then, but on the third page, they basically have this list of the different types of reactions that you can be looking at. For the purpose of this course, that's more than sufficient. And for the purposes of a lot of science, that's also more than sufficient. It's a really good tool for looking at these kinds of things. There we go. So the two that I really want to talk about are the Click one, which we've already talked about, and the other one that we're going to see a lot of is the Thione reaction. This one's falling a little bit out of favor, and that's probably a good thing. So, like most people, I'm teaching things that were important 10 years ago but aren't as important today. This is definitely one of them, but it's still very useful. And the idea is that we're relying on the chemistry of sulfur and the presence of double bonds. So again, there aren't a lot of double bonds in nature. Now, they're not as rare as alkynes. Alkynes just really don't exist in the human body, not in way size. Double bonds, you've got double bonds. But not all that many terminal double bonds. They're kind of unusual in most human metabolites. Of course, we do have sulfurs. We have all the cysteines in our body. Every single one of those can do these kinds of chemistries. And that's why this isn't as useful as some of the other techniques. But if you want to snap something together, you don't really care where it goes, like just put it on a cysteine somewhere, this can work very well. So any double bond, any thiol, treat it with some light. You don't need to add any other reagent. And so what you do, essentially, is our poor sulfur atom has one of its electrons promoted into a higher orbital. So you kind of have a plus-minus situation going on. Because what you've done is you've taken a filled orbital with a lone pair in it, you promoted one of the electrons with the light. So you generated a radical. It's hard to draw radicals with sulfur because this is making use of the expanded valence shell of sulfur, and we're normally used to drawing carbons and oxygens and stuff. So we've got our box, and here suddenly we're losing our box. So we have one orbital, which is kind of positive because it's sort of missing an electron, and we have another orbital we can think of as kind of negative because it has an electron which it wasn't expecting. This generates a radical. This radical, of course, reacts with something. What's a weak thing to react with? Double bonds. I guess it's tone neutral. But we still have this sort of extra electron here. And then this just rearranges through hydrogen abstraction. To give us a neutral molecule. So basically you take specific wavelengths of light, you shine them on sulfur or thiols, and boom, it clicks, and you make the bond. It's actually very, very efficient chemistry. The other one, the one I really, really love, I just love this chemistry, is down near the bottom of the table. It's tetrazole Diels-Alder. I'm looking for an excuse to use this because it's just so beautiful. So you take any double bond. It doesn't even need to be an activated double bond, which is pretty awesome. And you put that near what's called a tetrazole, tetraazole, so it's got 4 nitrogens. And the first thing you should be thinking whenever you see a molecule with 4 nitrogens like that is, how can I make it into nitrogen gas? Because, again, it is what everything wants to, it's what all nitrogen wants to be when it grows up, is become nitrogen gas. So if you remember your Diels-Alder chemistry, those of you who haven't taken it, that's cool. What we're going to do, but you might want to just take a quick look. Just going to count atoms. And I'm going to use the electrons in the 1,2 double bond to attack carbon 6. The electrons in the 5,6 double bond to attack carbon 4. And the electrons in the 4,3 double bond to remake a double bond between 2 and 3 because 2 just lost some electrons. So these are generally called pericyclic reactions. Samra was talking about these last class, that these are very efficient click reactions, and that's because, like the thione we just saw, and like the copper azide alkyne reaction, every atom that's in the starting materials ends up in the products. Except here that's not completely true, but Diels-Alder's that's absolutely true. So there's no waste, there's no leaving groups, there's no protons that are being lost, there's no water molecules being lost or something else. every atom ends up there. So if we draw the product of this, it's a little awkward. I'm going to actually just draw the nitrogen atoms that we have, kind of as a bridge. It's two nitrogens. It's not completely clear from how I drew it. Nitrogen, double bond. And then we have the new 6-membered ring that we just made. And then our other ring over here. Now this is where this gets really clever. So, and there might be some R group up here. Whatever. R group, you can stick the R group anywhere you want. I guess it can't be on nitrogen, so it has to be on the 2 carbons. The starting material, the tetrazole starting material, was aromatic. So it was very stable. Like, you look at it, it's kind of like benzene, right? We've just swapped out a couple carbons for nitrogens. It's aromatic. But it's not as aromatic as benzene because not all the atoms are the same. So you don't have as much aromatic stability as benzene. And that's why it reacts. Like, benzene doesn't do Diels-Alder reactions because it just looks at a dienophile and goes, yeah, or a dienophile. It looks at a double bond and just goes, yeah, I'm not going to do anything with that. I'm very happy being benzene. Whereas these tetrazoles are much more reactive, much less happy. Tetrazine? I can't remember if it's tetrazine or tetrazole. Maybe it's a tetrazine.
John?
Yeah.
What stops the lone pair from the nitrogen from reacting with the diene?
Well, with the double bond or the...
Yeah, like what stops like nitrogen 2 from attacking 6?
Nitrogen 2 is not really nucleophilic, right? And 6 isn't really electrophilic. Like, what we're doing here is, this isn't like, I've drawn it using lone, like, arrows like this, but if we remember how these things work, I've used the impoverished language of ionic chemistry, which is 2 electrons move, to try and describe something that's not really happening through ionic chemistry. We're happening through orbital rearrangement. And it's because that 6-5 bond isn't polarized. Like, you can mix like things with double bonds in them in amines, and they don't do anything. They just sit there and stare at each other. So what's really essential is the availability of the orbital systems. And I don't want to get into FMO theory today because it's going to take up the rest of the class and we need to cover other stuff. So I'm actually going to decline to get into that.
No worries.
But if you like, I would just take another look at the Wikipedia entry of Diels-Alder if you need to just refresh your memory.
Yeah, no worries.
But what really happens cool here is this was a Diels-Alder reaction. We had a diene and a dienophile. A diene was this guy with the 2 double bonds on nitrogen. Dienophile is something that loves dienes. In this case, it's just double bond. This is not a massively variable reaction, one I just showed there. It can happen. It's not super favorable. What is super favorable is what happens next. So we do a retro Diels-Alder. So a retro Diels-Alder is not a Diels-Alder that happened in the 1980s. It's a Diels-Alder that goes backwards. And that is a really bad joke, and I promise never to use it again. And the driving force here is just, you made nitrogen gas. And I think we've talked about this a bit throughout the course so far. Making gas is a good thing. You can generate gas, that's amazing. And so this is a massively favorable reaction to occur because the first step, not super favorable. I actually think that this is actually an unfavorable reaction. The second step, though, is massively favorable because of gas. So this is an incredibly selective reaction. You got to keep that poor, I'm really leaning towards it being called a tetrazine, and I'm probably still wrong on that. It probably has some stupid name with a P. You got to keep that away from double bonds all the way through its synthesis, because as soon as it sees double bond, it does this thing. So the other one I want to touch on, but again, what we've talked about so far are 3 irreversible click reactions. Once they go, they do not go back. And irreversibility is one of the, I would consider it kind of a general principle of click chemistry, in that you need a massively thermodynamically favorable reaction. And massively thermodynamically favorable reactions are, by definition, irreversible because, you've got, because favorable reaction means product lower than starting material. By definition, irreversible. So it's nice to potentially have a reversible click reaction. And there's 2, I think, that are worth considering and are related. One is imine formation, or so everybody tells me. I do not have a lot of luck with this one either. But theoretically, we've actually seen this already in the course. You take any secondary amine, you add it to any ketone or aldehyde, you dump in a bit of acid, you lose water, and you make an iminium. Very favorable if no water. Reverse it by putting it in water with acid. So it's a reversible reaction, which is kind of handy. The second one is a little less reversible, and it's related, and it's oxime formation. I spent about a year trying to make degradable rubber using this chemistry. I could never get it to work. So again, this also doesn't work for me. But there's really, really good chemistry out there where people have done really cool things with this. It's exactly the same mechanism we just did. Well, I didn't do the mechanism, but it's exactly the same mechanism we didn't just do. I guess you can lose the hydrogen. So one of the questions, the reason I'm covering all this stuff is one of the questions in assignment 5 asks you to use bioconjugation chemistry to attach pieces together. You can use whatever of these you like, combine them however you like, do whatever you like. You're going to want to make sure that the approaches you use are orthogonal to one another. So you can't use two chemistries that both need double bonds and say, hey, look, magic means one of them uses it and the other one doesn't at this time. So the thione and the tetrazine stuff can't both be used if there's double bond present, because you can't protect one double bond in presence of the other. But other than that, you're free to use any of these things for that, or anything else that you find. I'm happy if you go into the literature and you pull something else out that you like. That's absolutely fair game. Some of these questions are designed to make you go into, like, a lot of them are designed to make you go into the literature. So I think the last click reaction I really want to cover brings us sort of back around to where I want to touch on next, which is peptide cyclization. Well, you know what? Before I do that, okay, we'll talk about another click reaction. We'll talk about it in terms of peptide cyclization a little bit later. I think before I do that, again, teaching towards the test, I want to talk a bit about dendrons and dendrimers. Has anyone heard of dendrons or dendrimers before? Cool.
Yep. Sorry,
Oh, yeah?
I couldn't get my computer to unmute. Yeah, we learned about it in the nanomaterials course that
Oh, cool.
Simon's teaching. Yeah.
Awesome. Okay. So that's you and Susanna.
I think
Yeah.
Trisha's course might have talked about it briefly, like her materials course. I can't remember though.
Great. Okay. So, anyone remember what they are? Do you know them when you see them?
Yeah, I would say it's more of a no when you see it
Yeah, that's
type
okay.
situation.
So I think there's a whole bunch of these. So what the difference is a dendron. They're often called hyperbranch polymers. And a dendrimer it's kind of a cluster of dendrons. Or you can think of a dendron as part of a dendrimer. So what do I mean by this? Well, I'm going to focus on dendrons here because I think, unlike a lot of, I think unlike my colleagues, I'm more interested in dendrons than I am in dendrimers. And so what a dendron has, I'm going to start a new slide. Probably should have done it at the beginning. Oh, okay. Now I'm going to have trouble with this. Okay, there we go. So a dendron has a focal point. It's a stupid name, but the overall idea is that there's a central point that everything is building out of. Then you build a polymer from it, but your polymer has two or more identical components to it. So a normal polymer is completely linear. Like, a normal polymer, you have A, A, etc. Normal polymer. A dendron, your A has 2 points where it can make a connection, plus a link back to the focal point. So it's a polymer. It's the same thing over and over again. except it's branched. Now, one of the neat things about them is, like, unlike normal polymers, we can generally make these monodisperse. Which is a fancy way of saying only one thing is in there. So most polymers by definition are polydispersed because of the way they're made. Normally when you make a polymer, you mix monomers together, you stir it for a bit, and you get things of different lengths. Maybe you focus in, maybe almost everything is 500 units long, but you'll have stuff that's 499 units, you'll have stuff that's 501 units. Whereas with a dendron, we can actually get something that is all the same size. And we're going to talk briefly about how to make these kinds of things and two different classes of them, why you do that. A dendrimer arises when you have a bunch of dendrons, which then flex out from a central point. It's kind of like a dendron of dendrons, except you lose that distinct focal point, because for you have a very distinct center, but for a dendron, this is functionalizable. For a dendrimer, it's not. You have the same thing going out in every direction. It's a really good nanoparticle, really useful for that. Sort of. I was talking with the guy who, it's a weird thing. There was somebody who actually invented these because these don't exist in nature. So I was talking with the guy who invented them back in the 90s. He invented them in the 90s. I didn't talk to him in the 90s. And we were chatting about this because I was using dendrons for some of my science. And he said one of his greatest disappointments is it's still a technology that really hasn't found an application. There's no use for it. Like, polymers are really important for everything. Dendrons still aren't very important for anything. They are kind of popping up here and there. And there's always this promise that it's going to be the next drug is going to be a dendron drug, but that never never really happens. And so it's a technology that's looking for something to do. I still think it's really useful. And I'll talk about why. But first, let's talk about how to make some of these things. So there are lots and lots of different dendrons. You could go out there and design one if you like. There's three I want to talk about. I'm going to start with a natural one, polylysine. So when we think about the dendron, what you need is three functional pieces. You need two of them that are the same, and one that can link back to the previous step, the previous core. And so if we think about lysine, we've got that. Now, it's not symmetrical, so it's not a symmetrical dendron, but no one said it has to be. That's not one of the rules. Like, it's got the right stoichiometry, internal stoichiometry, 2:1. It's got two nitrogens, one carboxylic acid. And so you can imagine, let's say we took lysine and we protected the carboxylate. Let's say we took, I don't know, benzyl alcohol, strong acid, heat, do a Fischer esterification, boom, protected it. You wouldn't do that. It's stupid, but it works on paper. Mostly you wouldn't do it because you wouldn't want to be distilling off benzyl alcohol for the rest of your life. And now we take that and we treat that with a different one where we have a free carboxylic acid. And let's say we have Bach groups on both of our nitrogens. Since you want to talk about this with peptide chemistry, because this is just a peptide bond we're making, you could use HCTU, if you like, to make the bond. You're making a bond between a carboxylic acid and an amine, except you're doing two of them. So you have this CO2 benzyl. You've got one and two new lysines attached to it. And just a little note here. Note that I drew a down wedge here. I normally, if you have the nitrogen to the left and a carboxylic acid to the right, and a side chain up, it's an up wedge in all the natural amino acids. If the carboxylic acid is to the left, then you flip this thing over and you shove it down the wedge, unless you're using unnatural amino acids. But if you're making a dendron, I don't know why you're spending 1,000 times more on an unnatural amino acid. So just do watch that stereochemistry. Anyway, so what we've done is we've gone from 2 times amine to 4 times amine. No, I don't want to set up my pen. But we're not quite there yet because we don't have amines yet. We still have them protected. Use deprotection strategies we learned from peptide synthesis. We can use TFA-DCM. And then what we end up getting, I'm going to just stylize this. And you're very welcome to too at any point once you've sort of drawn this, because you don't really want to have to redraw that damn thing over again. You've gone now back to, now you've got your 4 times amine. Okay, so just a bit of terminology here on what we have. We would call, so normally when we're talking about dendrons, we're talking about two to the n functional groups. So here we had 2, here we have 4. This is n equals 1. This is n equals 2. So I would call this a first generation dendron. And this would be a second generation dendron. You get a third generation dendron by doing this again. The other thing I want to point out is if we go back to the solid phase peptide synthesis, and we thought it's really straightforward, it's really easy to do. What you do is you couple an amino acid, you deprotect. Now you couple the next amino acid, now you deprotect. And it's exactly the same pattern here. And it's actually exactly the same chemistry. It's exactly the same reagents if you're doing Bach solid phase peptide synthesis. You couple an amino acid, you deprotect. Then you couple the next one, then you deprotect. It's exactly the same sequence of things. But nobody in their right mind uses polylysine to make dendrons anymore. They are really useful if you want a biocompatible type of dendron because it's lysine. but you do get real complications because you have asymmetric geometry, and that can cause real trouble with the shape of the dendrons that you get and dendrimers you get. They're really ugly, and they don't behave quite the same because, yes, these are both nitrogens, but it's not going to be too surprising that after a few generations they no longer behave the same, because one is just going to be a whole lot more hindered than the other one. So ideally what you want is you want symmetry all the way through. So this takes us to Donald Tamalia's Pamam Dendrimers. Which he had before Hunger Games. That's really similar. And what he realized is this whole amine chemistry is really quite handy. Nitrogens are great, but this is a bit of a pain in the ass with this coupling reagents and stuff. So we want to make these with click reactions if we can, instead of with okayish reactions like peptide coupling, which is still really, really good, but you need to couple everything. Things are a little bit different, and everything's a little bit different sized. So what we're going to realize is that a lot of this stuff relies on kind of two building blocks in a lot of cases. And we're still going to do these kind of two-step things. Like, keep that in mind. Because it's the minimum number of steps you can use. Otherwise, things are going to react to themselves uncontrollably. You kind of need to have a protecting group or something like that. But you don't want more steps than you need. So if we take an amine, and we take acrylate, now the lone pair on a nitrogen is going to attack the carbon. And that's because the acrylate is really, really, really polarized, right? Like, it's a great myco-acceptor. If you need to look up myco-acceptors again, not a bad idea. I guess myco-addition chemistry. So you can get something like this. But the cool thing about primary amines is they're not done after doing one myco-addition. They want to do a second myco-addition because they still have an acidic NH. Note I just did a proton transfer. I just got rid of the offending hydrogen that I didn't want to see. You guys don't need to draw that either, because it's a waste of your time. I assume you can keep track of protons. If you screw it up, that's on you, but if I screw it up, I can always go back and fix it. I guess you can too. You got all the time in the world to do this. Okay, so you just did a double myco-addition. Of course, I've drawn a weird tautomer of this thing. I've drawn the enolate. The enolate is going to quickly, of course, equilibrate to the ester. Okay, but we're not done yet, right? This is kind of the coupling step. But we haven't regenerated the right chemical functionality that we need. And the chemical functionality we need is an amine. But luckily, this is really easy to do. You take ethylene diamine, and you transamidate. Basically, you make an amide from an ester, which is really favorable because amides are much more stable than esters. Otherwise, all of our peptide bonds would be always falling apart. And they're not. And oh, look, you've regenerated a primary amine, which can then make the next generation of the dendron, because it can do 2 microadditions now. And unlike the lysine, you got symmetry. And so this is really favored because of that symmetry. Now it's also using 2 really efficient click reactions. The addition of strong nucleophiles onto microacceptors is incredibly facile. It works really well. And transamidation works really well all the time, unless, in this case, when you want it to. Most of my experience with transamidation is when I don't want it to happen. But it's incredibly, that works amazing too. The problem with PAM dendrimers is, and you'll never find it anywhere because nobody wants to come out and say it, they're toxic. Mostly, it does, there's a lot of discussion going on right now. It does seem to depend on what is on the end of the dendron. If you have free primary amines, they're really toxic. If you have free esters, they're toxic because they just end up cross-linking lysines in your proteins and doing weird things like that. It causes lots of toxicity and you die. But if you terminate them with something else, they don't seem to be as toxic. But then people are saying, well, if you terminate them with something else, if you stick something else on the end there, like, acetate. Stick an acetate on the end of all those nitrogens. So you have N-acetamides. That's non-toxic. But those break down into the previous PAM dendrimers, and then those are toxic. So there's a lot of push over whether these are really a thing, and they're going to be useful for anything. And so that's why we have a second class of dendrons I want to talk about. And these are called the bis HMPA dendron. The big guy in this field, if anyone cares, his name is Melcock. So really, he's in Sweden, but he's not Swedish. Karolinska, I think, Institute in Sweden. But I think this chemistry actually came from the Tamalia lab originally. It's just this guy's taken it and run with it. So the overall idea is pretty similar. Again, keep in mind that we're using that coupling deprotection sequence. And so what they start with is a molecule called bis HMPA. This, actually what they normally start with is this guy protected. I think we actually have like a 50 kilogram drum of this stuff in the lab. Because it's relatively inexpensive to buy. It's a bitch to make. So one of the big benefits of this is where our dendron generation is going to be added to. We're going to use those alcohols. This is our focal point. And so your starting material, you've got a lot of flexibility with how you're going to functionalize your focal point. so sometimes it can be a little bit harder with the PAM dendrons, it can be a little bit harder with the lysine because of the asymmetry. But this guy, you buy it all protected, it's all ready to go. And one of the most useful things to stick on your focal point is something that you can easily turn into something else. So it shouldn't be too much of a surprise that one of the most common things to see stuck on focal points is pipergylamine. And that's because that's going to set us up with an alkyne on that focal point, so we can do click chemistry with the focal point of the dendron attached to something else. This might have relevance for the assignment. So make that. Then we're going to do our deprotection acid. You know what? I'll be specific. Sulfuric acid and ethanol. Ethanol because it's not soluble in water, because look at it. Now we have the two OHs. But now if we look at this molecule and we look at that molecule, we need to make an ester bond between them. Lots of ways to do it. One of the most reliable ways is to use EDC, which we saw in our lecture, I think, which was like 2 of us on peptide coupling. The first one, we were talking about DIC and EDC and the other carbodiimides. And so do EDC and this guy. And you're going to need a bit of a base. And I always pick DIPA because I have no imagination. There's no points for imagination in base.
To be fair, it is a cool base.
It's a very cool base. There's a joke in there about music and bass lines, but I'm not going to make it because it'd suck. So, and now we've kind of propagated this thing now, and you can just do that multiple times. Now, the really, really key thing about this, and what's really weird about this, is if we look at this guy here, the methyl group doesn't seem to be doing anything important. But what it's doing is it's making sure that there's no alpha proton adjacent to that carbonyl, so that if you want to do some base-sensitive chemistry, you're not going to accidentally make some enolates. The other thing it does is it bulks up this center. So this carbonyl is sterically hindered, which stabilizes it. Because if you don't have that methyl group there, and you make this water soluble, the esters all fall apart in water quite quickly. But having that methyl group there increases the steric bulk around that carbonyl, and it stabilizes this molecule. Enolization. Prevents hydrolysis. I like to think somebody tried to make this first without that methyl group there and just ran into so much trouble. And then, some grad students said, look, let's try it this way. And they did, and it worked better. And then the professor pretended it was their idea all along. So that's, I think, what I want to say about dendrons. There's 3 main types of dendrons, or there are dozens of others. You could go find something else. If you want to make a different type of dendron for the question, go nuts. Feel free. You just need to satisfy those conditions of having 2 functional groups the same, 1 different, and a way to connect those together. And so you couple, deprotect, couple, deprotect, couple, deprotect. There are other ways of thinking about that. Instead of deprotecting, you can activate. Maybe it's an inactive functional group, and now you turn into an active functional group. But essentially, that's the same thing as deprotecting. It's just fancier. So I think that's all I have to say about Dendrons.
Do you have to use that amine for a protecting group, or could you use something like just like a traditional like benzyl protecting group or something?
Yeah, you can put anything you like there. Doesn't matter.
Okay.
Because what we're doing there is down the road, like at the end of this whole thing, I guess where I do want to say something more about Dendrons is at the end of the game, you've got your focal point, and then I don't know how many different things on the end. I think that's the third generation. It's 16. Well, that's fourth generation. I made one of those, and I still kind of have nightmares about it. But at this point here, what you can do is you can attach something here. So if you have an azide here, alkyne, non-azide, and you've got, I don't know, NH2s on the end here, then you could do click chemistry and attach something down here, like peptide. And maybe then you have a ketone attached to a sugar. So you could be doing imine chemistry on the ketone sugar and click chemistry. Oh, I clicked on something and something bad's going to happen. Here we go. And click chemistry between these guys. So we could end up with peptide, like a single peptide. I'm not going to draw it all out. No, I guess I will. It's kind of fun to draw these anyways. Sugars on all of these. So why would you want to do this? And the reason why is multi-valency. And I'm out of slideshow, so I'm just going to create more slides. And this is why I think it's particularly appropriate to be talking about, and this is why I'm talking about in a class about peptides and sugars, because a lot of the times when we're thinking about what we want to do with these things, on their own, I guess on their own, every molecule is useless. It's only useful if you're doing something with it. And a lot of what we do with these kinds of things, because they're so effing expensive to make, it's going to be medicine. There's really no way around that. You're not going to build a building made of peptide, synthetic peptide. It might be kind of cool to build a building made of natural peptides. It would be like a tofu igloo. But you're not going to make it out of synthetic peptide. So you're going to make drugs or do something like that. And all sorts of different things you could be doing with drugs. But one thing we're always thinking about with drugs is the IC50 of a drug. So inhibitory concentration 50, right? Lots of ways to measure that depending on what assay you've got. Where 50% are blocked. 50% of activity exists. Target protein. Not sure why I'm writing it in such a short column. There are probably better definitions of IC50 out there. Okay. So what determines the IC50 of a compound? What goes into saying how good a drug something is and how well something binds? I guess that wasn't a rhetorical question. I just wonder if anyone has any ideas on that. Silence. Okay. So I think what you've got is binding affinity. This is not a real equation, but it's times localization. So what do I mean by that? These are the two things you need to always consider. And there's a lot of stuff going into both of those terms. Binding affinity of a drug is everything from, the actual entropics or enthalpics of the binding of the drug to the target. Probably also has to consider that if there's any kind of competition or any kind of different changes in the way the protein folds or sits or anything like that. So there's a lot of stuff going into that term. And localization can be a lot of things. So does your drug get to the right place? Like you can have a drug, and this is a major problem we have, especially with my favorite example of this is brain cancer, which is a sad thing to say. So brain cancer is, depending on the brain cancer, mostly a death sentence. They're really, really, really dangerous. And often it's not because the cancer is particularly bad. If that cancer was occurring somewhere else in your body, breast cancer is a big common example. Breast cancer now is generally quite treatable until and if it metastasizes to the brain. And it's exactly the same cancer happening in your brain, but suddenly we're not able to treat it. And it's because we can't get the drugs into the brain. And so we have a localization problem. It's not that the drugs suddenly got worse, it's that we can't get the drugs to where they need to be. So for a drug to be good, it needs to be able to do two things. It needs to bind the target really well, and it needs to be where the target is. And if either one of those things is missing, it doesn't matter how good it is at the other one. Okay. So we can really start thinking down about the localization idea. So let's say you have a receptor. Like everything else in this lecture, it is a V. And you've got a drug. Let's say you've got two molecules of that drug. And there's a box that those molecules are in. Let's say that drug is at 1 molar. Just a number, drug concentration. That's a ridiculously high drug concentration, but whatever. 1 is a nice, easy number to work with. So, this receptor is blocked when a molecule moves in to occupy the receptor. And let's say there's an assay that we have, and we can tell the receptor is blocked. So molecule goes into receptor, molecule comes out of receptor. It's competitive binding, standard competitive binding kind of thing. And another molecule can come in, or the same one can come back. But those two molecules are spread out over the entire box. So once a binding event happens, and the first molecule kind of dissociates, there's no mutual dependence on that. You're not making the other molecule more likely to bind or do anything like that. And right now I'm talking gibberish. And that's because let's consider what happens if you have this as a dendron. Maybe this will make less gibberishy sense. So we do the same thing. But now these two molecules are tied together. Okay, so we're not changing the binding affinity at all. Binding affinity is absolutely the same. It's the same molecule, same warhead, same binding affinity. Of course, you change the binding affinity, attach it to something, you distort it a bit, but let's pretend the difference is minimal. That's often actually a pretty safe assumption. And we have the same number of warheads in the box. We had 2 warheads on the left box. We have 2 warheads on the right box. There's no box drawn because I just haven't drawn a box. There's a box. Same box. Okay. Which one of these two do you think is going to show a higher IC or a lower IC50? Lower IC50 is a better IC50. Could you talk us through why?
Would the one on the left have a lower IC50?
Okay.
Because on the right, you have one drug molecule with 2 warheads compared to just 2 separate drug molecules.
So 2 separate drug molecules is better.
Or wait, no, worse. Sorry, I
got
the IC50 mixed up.
Right, it's worse. And the reason is that on the left-hand side, if you think about the idea of drug binds to receptor, drug dissociates from receptor. And again, coming back to this localization question, the concentration is the same here. But when you have 2 of them tied together, the localized concentration right around the receptor when that drug dissociates is much higher because now I've got 2 of them held in close proximity to that receptor. Whereas over here, I have 1 in close proximity to the receptor and one like infinitely far away. So, molecule comes in, molecule falls out, comes in, falls out. But if you have a whole bunch of them around, one falls in, falls out, but then there's a whole bunch of others that are right there and available to slide in and bind. And so you get much, much stronger binding affinities when you use a multi-valency effect. It's because it can't get very far away before it's attracted back. We use multi-valency all the time in our everyday life, and I am currently failing at finding analogies. But, no, that's a disgusting analogy, and I'm not going to use it. It involved carving body parts up, which really isn't a good idea. I need to think on this. But the overall idea is that you're keeping things in close proximity together. And so you're keeping a high localized concentration right next to the receptor, even if your global concentration is the same. Your local concentration is infinitely higher. And this is how biology works. Like, this is how cells work. So I'm sure you've seen, you've seen the lipid raft bilayer on a cell. And so there's like a you got a surface, it's a cell, you got some proteins, you got some other proteins, there's some other colors, and they're all kind of mixed together. And what seems to be happening, like again, we're not sure of this yet. At least we weren't sure when I last checked. Though we have new tools now, we might actually be able to see it. Is that this is a completely inaccurate way to draw a cell? Cells don't do this. Cells are constantly forming areas of local order. They're called nano domains, lipid nano domains, because they're nano. These are transient. I have no idea what that word says. Transient structures. And the idea is that you would actually, on that thing, what you'd probably more likely have is you'd have a bunch of the blue ones all gathering together and a bunch of the red ones all gathering together. And so that when you have something else coming in, and orange binds with blue, you have a multivalent effect. You have multiple blues around there to bind with orange. You don't have one protein binding together. You got it so that when that drifts apart, it immediately latches onto another protein. And this is generally how cells interact with one another, is through these multivalent effects. And so taking advantage of multivalency through Dendrons is basically us taking, like everything, taking inspiration from nature and just running with it. So Dendrons give us easy access to multivalency. Monodisperse. Again, you can make all one molecule because it's perfectly branched. It's branched perfectly at every point. Everything's always attached. It's all one thing. The FDA loves it because it's all one thing. The FDA gets very upset when you have mixtures. They do not like mixtures. They like single things. Or Health Can, because, we follow the Americans on this for the most part for drug approvals. And I think that we're going to see an increasing number of multivalent drugs coming through, especially targeting some really, really hard and difficult indications. So it's pretty exciting, actually, to kind of be doing science at this time when this idea of multivalency is really starting to grab hold. And we're seeing a lot more of it. And it's because this is how biology works. So if you want to create a drug like that, you don't need to maximize binding, because you can rely on multivalency if you set that up and you set up your structure properly. So I think that's where I wanted to get to today. Introduce the idea of multivalency. This is just an overview that dendrons exist. There's 3 common types that you can use. Multivalency is a thing. I could teach an entire course on multivalency and the different aspects of it in chemistry, but that's not what we're doing here. And I think that it's really, really important, especially with how cells use sugars and amino acids and peptides and proteins to talk with one another. Like, you'll often see that so many protein interactions recruit multiple copies of the same protein. They do tetrameric formations and things like that. And we have some click chemistry that allows us to selectively snap on many, many copies of sugars or peptides onto dendrons with high efficiency, because we have these different reactions. So that's how all this stuff ties together. I think we have next class, we're really looking forward to a presentation. And then the last class is next Tuesday. And we're going to talk about peptide cyclization. It's the last subject I haven't covered yet. And then we're done. I'm going to, like, over the entire exam period, I'm happy to provide, point you in the right direction on any of the questions. Give you some literature stuff that if you're really stuck and need something to go, then want to give you something to read on that. That's good. Yeah. I'm going to go get some sleep.
Good call.
Yeah.
I'm gonna go pack.
Are you moving?
Yeah, like half moved. We're doing the final boxes tomorrow and then furniture the next day.
Moving sucks.
Yeah, it fucking does.
Yeah, that's right.
I'll get through it.
Yeah.
Thanks, John.
All right, bye everyone.